Audio Jungle. Audio Jungle.
It's a thermodynamic relation. What is that? We know one very famous relation which is called the Mayer's law. So it is nothing but Cp minus Cv is equal to R. Yes or no? Where R is nothing but Ru by M. Okay? R is nothing but Ru by M. Where Cp is specific heat coefficient at constant pressure specific coefficient at constant volume. All right, and what is the R? R is characteristic gas constant. Yes or no? Characteristics gas constant. You all know all this relation, but here again I am explaining this so that you can relate, because now the in the problem, like we'll solve the problem here. So in the problem, direct this relation will come, okay, and you should know, otherwise it will be difficult to solve the problem sometimes. Okay, what is the Ru? It is universal gas constant. It is called universal gas constant. Yes or no? Now we all should know the value for the, because here we are going to talk about the air. Okay, so for air, okay, I'm not saying oxygen, air is the basically gas, you can say. Yes or no? So or simply you say air, there should not be confusion, because for the gases gamma value will change, because gas can be at different temperature. Suppose at the exhaust of the nozzle, so that time it will not be air, it will be gas. So that time gamma Cp value will change. Okay, so all value I am going to write directly here. For air, what is the value of Cp? Value of Cp I will write here. Cp for air, okay. It is nothing but 1.005 kilojoule per kg Kelvin. You need to remember this. Cv of air is nothing but 0.707, or sometimes it is 0.718 also. You may have seen some in few books. Generally it is 0.707. Okay, that value you need to remember. It is 0.707 kilojoule per kg Kelvin. This is the value of Cp and Cv. All right. And what is the value of Ru? Ru is the universal gas constant. It is 8.314 kilojoule per kg Kelvin. What is the M? M is nothing but, for air it is 29. What is the M? Molecular weight of air. Okay. So if you do that, then you may have R value. What is the R now for air? Because universal is what constant, it is not going to change. But this air R value will change because molecular weight for the all the gases or elements value will be changing. Okay, so definitely R value will be changing in that condition. All right. So if you do this, how much you may get? Here is my calculator. Can you tell me what is the value? Here. It is 8.314 divided by 29. It's 286 point, because this is the kilojoule per kg Kelvin. Okay, so now you have multiplied by 10 to the power 3, so joule per kg Kelvin. This is the value of R. All the data whatever I am writing here, it is important, so please make a note because you have to use this for further calculation and all. This is the value for air. Okay, all right. Then another relation what we have, it is nothing but formula of Cp. Okay, sometimes Cp will not be given in the problem, you need to calculate what is the Cp. It is as I told you, Cp minus Cv, it is R. This is formula number 1, and second formula is what? Cp by Cv. This is nothing but gamma. What is this gamma? It is called specific heat ratio. What it is called? Specific heat ratio. Yes or no? Specific heat ratio. Okay. Gamma for air is nothing but 1.4. How to calculate this? You can get Cp 1.005, 0.707. So if you do this, zero 0.718, just wait. It's make it this value 0.707 I have written. You make correct this value 0.718. Okay, 0.718, 0.7. But in few books I have seen 0.707 also sometimes, but nothing to worry. This value you may get 1.399. So generally for air it it is 1.4. okay, this value also you need to remember. All right, this is the formula number 2. If you solve this both formula, okay, Cp minus Cv is equal to R, Cp by Cv is equal to gamma. If you solve both equations, then you will get Cp value. This is nothing but gamma R upon gamma minus 1. You can solve by your own, okay, and Cv is equal to R upon. So sometimes they will not give the Cp and Cv value, they will give R and gamma value, and you need to calculate that time. I always used to tell this, don't believe this value, okay, Cp and Cv value. If it is air, then only this number will be there, okay, otherwise you need to calculate. How you will calculate Cp and Cv? By this formula. This is valid for any type of gases. It is air or carbon dioxide or any gas, nitrogen, whatever the gases are available. For that, if R is known and gamma is known, then Cp and Cv you can calculate. There is no doubt about it. Okay. Always remember. So these are the values. Now we'll go for the next parameter. These are the parameters definitely will be using in numerical and all. Okay. So anyway, now next parameter is what? Mach number. Okay. So what is the Mach number? It is a non-dimensional number. Yesterday only I had given that formula to you. This was m is equal to v by c. V is the local velocity. V and c is nothing but, for isentropic flow it is gamma RT. Okay, Mach number. Actually it is, the formula is what? Inertia force. Inertia force by what it is called? Viscous force. No, elastic force. Inertia force elastic force, sorry, not viscous. If you are writing viscous, then it will be Reynolds number. If you solve this, then you may get. So generally this is the formula of the Mach number. This is also very useful. You are going to use this. Where c is what? C is speed of sound. And what is V? Local flow velocity. All right, always remember. Now if you talk about this speed of sound, c is equal to what? Now I am talking about only for isentropic flow. So here I can write also, and generally until unless they are not saying isothermal, you have to consider it is isentropic flow. Okay. What is the isentropic? It is reversible flow, reversible adiabatic. Okay. Now check, this is C is equal to what? Gamma RT. Now you can write this formula as gamma, and what is the R? R is what? I told you, RU by M into heat temperature. So C, what is the speed of sound? You just focus here. Speed of sound, I told you, it is nothing but one more time I will write. Gamma is what? Cp by Cv. RU by M and T. What is the speed of sound now? Conclusion for single Mach. Single Mach, it is nothing but T is directly proportional to gamma, which is specific heat ratio. Okay. C, speed of sound is also directly proportional to universal gas constant. Okay. Speed of sound is what? Inversely proportional to molecular weight. Okay. Molecular weight. I am writing M. Don't consider it is Mach number. Molecular weight. Let me write this. Molecular weight. And this is also the directly proportional to temperature. What temperature? It's a local temperature or surrounding temperature. Okay, surrounding temperature. And especially it's a static temperature. Static temperature. All right. These are the parameters, and obviously it is root. So my intention not to tell this like formulation. I am just saying like, okay, if molecular weight is what going to change, then C will change. It is like in under root format or quadratic or you know uh, like a cubic. It's not my point. My point is, if molecular weight is going to change, then the speed of sound is what going to change. That you have to take care, and you have to remember this formula in this way. Okay. You can think like, if obviously temperature is what increasing, then speed of sound will be increasing. It will be changing. If temperature is what going to decrease, then speed of sound will decrease. Okay. It's very clear. In practically also, like winter days and summer days, you can feel that if temperature in summer days it is 40 degrees Celsius, 45 degrees Celsius, so what will be the speed of sound? And suppose temperature is what, 10 degree or 12 degree. Okay, so that time what will be the speed of sound? Even you can feel. Okay, it's very simple. Fine. So here you have seen that Mach number, which is nothing but this inertia force by elastic force. Okay. And already that regimes I told you, when Mach number will be less than 1, greater than 1, all the condition I told you, so no need to tell again this one is very clear. Now we'll go for the analysis, which is called isentropic flow. Yes or no? For the isentropic flow, we need to calculate the value for I mean that relation between total and static value. Okay. So total and static. So how to get this? Very popular energy equation we have. Okay. So from that energy equation we can get the isentropic relation. So better I will start this energy equation first, and from the energy equation we can get the uh, result, which is called relation between static and total. It may be static temperature and total temperature, it may be static pressure and total pressure, anything can be possible. Okay. Now we'll go for it. So what is the energy equation? Okay, energy equation basically, if you say, then we'll find it. Generally Bernoulli equation we know, but in thermodynamics, if you heard one terminology called steady flow energy equation, SFEE, yes or no? SFEE, which is called steady flow energy equation. steady flow energy equation. Okay, how to solve this? It's very simple. We'll make one system, and for that system directly I will write the equation. Okay, so this system is nothing but like this. This is the reference. Okay, this is the inlet, this is the exit. System, surrounding and boundary might you heard. So anyway, if you are making this system, so for this system I'm saying there is the inflow, which is nothing but velocity v1. This is the outflow where the velocity will be v2. From here this height is what, z1. So you can write potential energy, this is what, z2. Okay, obviously if you are adding heat here, you are adding heat here, q, so it will produce work, it will produce work, and this work will be the shaft work. Okay, ws, which is the shaft work. I mean, just like a steam engine, if you are adding heat there, so that heat will be used to produce shaft work and rotation you may get, and because of that you have seen the concept of a steam engine. Okay, so it is based on that only. Right, and obviously if you are giving the heat, so enthalpy will rise, h1 and h2 enthalpy will rise, yes or no? So I can write the equation, and this equation is what, use first law of thermodynamics for steady flow. Okay, using, because first law is what saying energy is what conserved, so based on that I'm just writing this using first law of thermodynamics. Okay, what is the first law of thermodynamics? Energy is what conserved. What is the energy? Let me write here and you please check. So you can say first, obviously kinetic energy will be there, so I'm writing kinetic energy. What is the kinetic energy? 1 by 2 mass flow rate, which is constant, so mv1 square. Okay, potential energy, because this inlet is what, from the reference there is the height, so potential energy you may have mgz1. Okay, you are adding heat here, obviously if you are adding heat then enthalpy will rise, or enthalpy will be there, h1. Similarly, same you can write for the exit also, not m2, it is constant mass, plus ws plus h2. This is the formula. Okay, this is the formula where, in short, I'm just writing h1 and h2, it is the enthalpy. Okay, kinetic energy at inlet and exit, q, heat addition and shaft work generated. Okay, please remember this. Now, so in this equation what we have now, Okay. We can consider what we can consider if there is the compressor or turbine, so that time there will be shaft work, because shaft work in the sense there is the rotation comes into picture. Okay. But if it is a static, okay, if it is a static system, there is no rotation, so what will be the shaft work? Shaft work will be 0, indicates no shaft work. I mean, if there is no shaft work, it means there is no compressor and turbine. The simple meaning is. But it's not meaning always there will be zero shaft work. No, if compressor and turbine is there, or anything, compressor or any compressor or any turbine is there, then definitely shaft work will be there. You cannot make it zero. But here I am considering it's a static system. We don't have any rotation and all. Simple flow is there. There is no rotation. There is no shaft work. I am considering, hence it is zero. All right. I am considering adiabatic flow. So I can say if it is adiabatic flow, then what will be the heat transfer? Heat transfer will be zero. Why? Because adiabatic flow. I am considering it is adiabatic flow, so no heat transfer. No heat transfer. Okay. Obviously, I am considering it is on same level. So Z1 is equal to Z2. I am considering it is on horizontal. If it is on horizontal, so it will be inlet and exit will be on the same level. Yes or no? It is on horizontal plane. So now what is the energy equation? Check. What will be this energy equation now? You will have 1 by 2 m v1 square plus h1 plus h2. All right, this will be the equation now. Okay. Now I am considering here this is the my final equation. Okay. Fine. Now I can say there are 2 points, inlet and exit. Second point I am considering, there is the velocity comes to 0. Second point I am considering, velocity comes to 0. Hence I can write, since point 2, considering zero velocity, that means v2 is equal to 0. If v2 is equal to 0, then what you may have here, check, it is 1 by 2 m v1 square plus h1 is equal to what? Velocity becomes 0. When velocity becomes v2 becomes 0, then h2 will be replaced by h naught. So I have written h naught, because there is no point 2 now existing, so we are considering this m and v1 as simple v we can write. Okay, it's our choice what we want to write, but I'm saying like second point is what not here, so we can say okay, now v becomes v1 becomes v, okay, and h1 becomes h. This is what h naught. All right. Now what is the mean of it? Meaning is very clear. Meaning is this enthalpy will be called as stagnation enthalpy or total enthalpy. This enthalpy is called as static enthalpy. Okay, static enthalpy. All right. Now, and this is what obviously kinetic energy of flow. Okay. Now, so we can say this H naught is equal to H1 plus half mv square. So this is what total enthalpy. This is what static enthalpy. This will be the kinetic energy, but in terms of enthalpy, it will be called as dynamic enthalpy. Why I am saying, because this right side is what enthalpy, even though this H is also enthalpy, so this should also be equivalent to the enthalpy. Yes or no? Hence, this kinetic energy can also be called here dynamic enthalpy. Okay, which is nothing but kinetic energy. Okay, so now in terms of specific, in terms of specific, how to write a specific parameters? You just, specific means you just divide by mass. If I am saying a specific total enthalpy, I am just going to write a specific enthalpy, then it will be H naught by m H by m. Okay, by m. So what you can write here, this will be now H naught, this is H plus H square. This is what is the difference here? This is in terms of specific, okay, value. This is what total value. See, this is the total, this is the total, this is the specific. Hope you understood. Total enthalpy and specific enthalpy. Now you got the difference. Yes or no? Total enthalpy and specific enthalpy. Hope you understood the difference. Fine. So this formula is very special to you now. H naught is equal to H plus V square by 2. Okay. For the case when gas is perfect, you know the formula, H is equal to what? CPT. Huh? Enthalpy is nothing but Cp into T. This is the one formula you should know. This is in thermodynamics. It is already given. Na? So directly I am taking this formula. Actually, it is the formula which is given in thermodynamics. But I am believing that you guys know H is equal to CPT. I can transfer this now. So this is H naught, hence this formula will be what? CPT naught, H will be CPT plus V square by 2. Yes or no? V square by 2. So this formula, what I am writing here, this is the formula basically the relation between the total and static. T naught is the total temperature, small t is the static temperature. So this is the relation between total and static. Yes or no? Total and static. Now, how to relate this in the airfoil? If I am going to write this in the airfoil, then how to relate this? So you can give heading derivation or relation between total and static quantities. Okay, how to relate it? It's very simple. I am just considering this is the airfoil. Okay, now we have flow here. This is the flow. Okay, I can consider 2 points here. This is point number 1 and this is at this, exactly at this. This is point number 2. Okay, so what will happen if you show the flow pattern? So that flow will go like this. Yes or no? Now this point directly it will go and hit here. So this point will be called as the stagnation point. Why it is a stagnation point? Stagnation point is the point where the velocity of the flow comes to zero isentropically. Okay, so I am considering here the flow velocity is what v1, here flow velocity is what v2 at point 2, but at 2 it is a stagnation point, hence v2 becomes 0. So if we apply energy equation, I can consider this is v1, hence this part here enthalpy is what h1 and here it is h2. Now h2 becomes h naught y because v2 becomes 0. So same thing you can write here in terms of h1. See this formula you can use. What formula? Directly this formula you can use here. Check the formula. This is the formula. You can use this. In specific form also you can write, just divide by mass, then what you will get? You will get h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. So this is what energy equation, and you should know this is the energy equation. You should know properly how to use this. h1 plus v1 square by 2 is equal to h2 plus v2 square by 2. You have applied energy equation between these 2 points. Okay, if you apply energy equation between these 2 points, so this point 2 you will consider as a stagnation point because that flow go and it will hit and it becomes 0 isentropically. So this thing will happen. Now the same like equation what you have derived earlier, you may get h v square by 2 is equal to h naught. And yes, this is the Bernoulli equation. Okay, this is the Bernoulli equation only. But the thing is what Bernoulli equation we have two, one for isothermal, another for isentropic. So as I in the starting only I told I am going to write for isentropic flow. Okay, if you go for the Bernoulli equation, so Bernoulli equation you can derive for both, for isentropic and isothermal. So this is for isentropic, not for isothermal. Okay, because isothermal it is not used anyhow, because if you go for 1D flow then it will be isentropic. Okay, So no need to write that Bernoulli equation for isothermal process. All right. Anyway, now this is the energy equation or Bernoulli equation basically here. So I can write now further in terms of temperature. So this will be what? Cp T plus V square by 2 is equal to Cp T naught. So what will be T naught here? Check. T naught will be what? Cpt divided by Cp plus V square by 2Cp. So T naught is nothing but T plus V square by 2C. Or you can say T naught is equal to T in bracket you can write 1 upon V square 2Cpt. This formula you can write. Okay. So basically this is the relation T naught by T. What you got here? 1 plus V square by 2Cpt. This is the relation between static and total. T is the static temperature here. T is static temperature here. And T naught is the total or stagnation temperature. Okay. So this is the final formula you need to remember. But this formulation what you have, you can also write in terms of Mach number, because Mach number is what very frequently used actually. Okay, very frequently used. So you can consider it that formula in terms of Mach number. So here you can say relation in T naught, T and Mach number. Now this is Mach number, don't say this is the molecular weight. Okay. How to develop this relation? It's very simple. Now you have P naught by T is equal to 1 plus V square divided by 2Cp. Here you can write 1 plus V square 2 into Cp. What is the Cp? I told you it is gamma R upon gamma minus 1. In starting only I told this. Okay. Cp. Now anyway, T naught by T is equal to 1 plus V square 2 upon gamma minus 1 and gamma RT. Okay. Next, you can write T naught by T 1 plus, check what it is, V square. In denominator, it is 2 upon gamma minus 1. You can take upside, so it will be gamma minus 1 by 2. Okay. What is V square divided by root gamma RT? So this gamma RT as it is I can write, so it is 1 plus gamma minus 1 by 2 into V square. What is root of gamma RT for isentropic flow? It was the, no need to write in, it is nothing but speed of sound, huh? Square, because what is the C? C is nothing but root of gamma RT, starting only I told you. So what is the gamma RT? It is C square. What is the Mach number? It is V by C. Okay. So you can write here T naught by T is equal to 1 plus gamma minus by 2 m square. V by C is nothing but m. This is very useful formula for 1D isentropic flow. Remember, this formula can be used only for isentropic flow. Isentropic flow. Okay, isentropic flow means reversible adiabatic. If it is not isentropic, this formula you cannot use. Okay, only for isentropic flow. This formula will be used only for isentropic flow. All right. So here what you have seen, this is the relation between the total temperature and static temperature in terms of Mach number. But it is not sufficient. Why? Because whatever the problem will be asked to you in examination, it will not be only in terms of temperature. They can also ask in terms of pressure. So here you can write relation between total and static pressure. Earlier it was this was the between relation between total and static temperature. Okay, this formula what you have seen, this is the relation between total and static temperature. Okay, now you are going to talk total and static pressure. How to write this? You know that very frequent formula. What is that? That called isentropic relation. Isentropic relation. I believe that at least basic thermodynamics you all know. Isentropic relations. What are the isentropic relations? It is I believing that you all know the basic thermodynamics. Okay. If any doubt again you can ask anytime, you can write. Okay. So P2 by P1 is nothing but T2 by T1 to whole power Cp by R. Okay. All right. What is the Cp by R? Cp is nothing but gamma R upon gamma minus 1. So if you check, this is nothing but T2 by T1. R cancel out, you may have gamma upon gamma minus 1. This is the isentropic relation number 1. What is the isentropic relation number 2? It is nothing but density rho 2 by rho 1 density T2 by T1. Okay, 1 upon gamma minus 1. Okay, these are the isentropic relations. So you can consider, you can say like that this is the airfoil here. Okay, or you can say this is what wing here. Now if you go and check the flow pattern, yes or no, like this. Okay, so why I am showing this airfoil, so it will be very easy to you to understand. Otherwise this airfoil is what looking good, so we'll keep this. That wing, actually it is wing. Okay, because once aircraft is not flying, so you will not talk about airfoil, it's a wing only. So here you have point. Huh? What are the points? Point number 1 and this is the point number 2. Yes or no? Point number 1 and point number 2. For the point number 1, you can say temperature is what T, pressure is what P, and density is what rho. velocity is what? V. Okay, at point 2, because velocity v2 you can say it is 0, so all the quantities, in fact enthalpy also I can write, all the quantities, temperature T2 will be T naught, because it's a point 2, hence I am writing point P2. Okay, and P2 will be P naught, rho 2 will be rho naught, and H will be H2 will be H naught. If enthalpy also required, you can write in this way. Hope you understood this. So I'm interesting to write the relation between total and static for the pressure. So what is the formula? Formula is very simple. You have P2 by P1 is equal to P2 by P1 to whole power gamma upon gamma minus 1. Check this formula. This is called isentropic relation. Okay. Anyway, what is the P2? Point 2 is P2 is nothing but P naught. Check. Point 2 P2 is nothing but P naught. P naught. P1 is nothing but P only. T2 is nothing but P naught. T1 is nothing but P only. It is gamma upon gamma minus 1. What is T naught by T? Just now you have derived here. What is this? 1 plus gamma minus 1 by 2 m square. 1 plus gamma minus by 2 m square to whole power, it is nothing but gamma upon gamma minus 1. Yes or no? So this is the final formula I am writing. This is the relation between total and static pressure. What is this? 1 plus gamma minus 1 to m square to whole power gamma upon gamma minus 1. This formula you should remember, it's very important. Okay, this is the relation between total pressure and static pressure. Now we'll write relation between total and static density. Check what is the rho 2 by rho 1 formula. Rho 2 by rho 1 is nothing but it's a T2 by T1. Na? T2 by T1, by mistake it is written. So rho 2 by rho 1 is nothing but T2 by T1 1 upon gamma minus 1. Yes or no? What you will do? You will simply write the formula. 1 plus gamma minus 1 by 2 m square to whole power 1 upon gamma minus. This is the relation. Rho 2 by rho 1 1 plus gamma minus 1 by 2 m square okay. So all the formulation whatever I am giving today, it's very important. Okay, this is the relation between total and static density. All right.